Let's talk about composite functions. For a quick review of functions, it is a machine that accepts one variable and applies to it some predefined rule, and transforms the variable into another dependent variable called the output. And every input variable that makes sense to the function machine is in the domain of the function, and every output that is produced by these inputs lies in the range of the function. Now let's consider two functions, namely function f and function g. Function f is a squaring function, so it squares every input from its domain and generates outputs. And function g is a reciprocal function, so it takes the reciprocal of every input that is given to it. And just to be more clear about the domain, consider the input value of 0 that do not make sense to the function g, as the output is undefined. So 0 does not lie in the domain of the function g. And let's arrange the function f and function g machines in a series arrangement. They are now in such a manner that inputting values to the function f produces outputs, and then these outputs are used as input values by the function g, and it produces final outputs. And if we surround the two functions by a big box, we have got a big machine in which we input values from one end and gets the output from the other, and we call it composite functions. And let's have a graphical interpretation of the composition. But first, we should understand what we mean by the notation f of x. This means that we are applying the function f on every input from the x-axis that lies in its domain, and similarly g of x means that we are applying function g on every input from the x-axis that lies in the function g domain. And with the same reasoning, the notation g of f of x means that we are applying function g on the f of x axis. But you may say, what do I mean by the f of x axis? As we know, the f of x is a graph itself. So the answer is, we can easily translate the f of x graph into a linear axis. And if we place the f of x axis and the x axis side by side, it is not difficult to see the relation between them. For example, at x equals 2, the f of x axis translates to 4. And we know it is correct as f of x is a squaring function, and minus 3 on the x-axis translates into positive 9 on the f of x-axis, and so on. Now if we apply function g on the f of x-axis, what we will obtain is a graph of function g of f of x. And let us move one step forward and also translate the g of f of x graph on a linear axis, and place it in accordance with the remaining x and f of x axis. And we can easily see the relationship between all the axes. For example, when we enter minus 2 as input from the x-axis, it translates to 4 on the f of x-axis, and that in turn translates to 0.25 on the g of f of x-axis, and so on. And now let us talk about the domain of a composite function. And it's easy to see on the screen that every input that is given from the x-axis at the end provides output from the g of f of x-axis after passing through the f of x-axis, or you may say the f of x-axis is an inner function. So if you input any x value that produces an error or undefined output at any stage of the translation, that x value is not in the domain of the composite function. As you can see, if we input x equals 0, we obtain an error on the g of f of x axis. So 0 is out of domain of the composite function g of f of x. And just to be clearer, the error can even occur in inner functions, and in that case also, the x value from which it was generated is also out of domain of the composite function. For example, if we change our composite function to f of g of x, or you may say swapping the order of the functions, now the error occurs in inner function, or you may say g of x at x equals 0. So 0 is still out of domain of the composite function f of g of x.